and they all come in. Like I've gotten 2 fortune cookies in one
Yeah,
packet.
I was about to say that 2 in 1.
I've got them where they don't get cut off, so I get like a string of like fortune cookies, each in their individual package. Yeah.
That's funny.
All right, well, let's go ahead and get started with binary search. We started on that algorithm on last Thursday. So by today, I think 50% of the class should have forgotten everything about binary search.
Everyone has fortune cookies. Some people like look at it before they eat it.
Right? I mean, does that sound about right? So we'll go ahead and just take a look at that file again, and this time I'll resave it into today's folder. So this way we have a full account of the binary search algorithm. All right, it already exists. Overwrite. No, I don't want to overwrite. I want to open, not save. Open. Pick the wrong key. Okay, so here is this is where we left off last time on last Thursday. And by the way, next week is spring break, and so we won't have class for one entire week. It's kind of a weird time to have a spring break, but since it kind of syncs with the middle school and elementary school, I cannot complain. All right, so this is binary search, and this is where we kind of left off from last time, where we say, okay, we have to assume some variable names. K is the value that we are looking for. I picked the name K for key, okay, because in search, what you're looking for is also called a key, okay? A is the array where we are searching in, and M is the index of the element that I'm examining in any particular iteration. There's a reason why I use M instead of I, because in this case M is kind of like the midpoint. Okay, so we'll figure that out later. And then what we did last time was to re-express the value is found in the array with a particular equation, equality here, because if K does equal to one of the elements in array A, we can get out, because that's a good enough reason for us to say, okay, I found what we're looking for. It is time to stop the loop, and we can exit and continue with whatever is next to the loop. Okay, we haven't figured out how to express the other one yet. All right, so this is where we were last time. And what I need to do is to resave this file into today's folder. So I'm going to make one first. Today is the 19th. And make sure I save the file again. Oops, save as. Go to the new file location. Yep, go ahead.
Just out of curiosity, if you have an even number of things on your list, which item will it take?
Say again? Oh, if there are two, okay, if there are multiple items, either one is fine. So we'll talk about that,
Okay.
as we try to work out the.
Will the language decide that? Or will,
No, the language will not decide that. You kind of have to decide it for yourself, because when you divide something by 2, potentially can end up with something 0.5. And if you do end up with something 0.5, then you have a choice of either rounding, just use the usual rounding mechanism, where if it is 0.5 or more, you round up. If it is less than 0.5, you round down. That will work in this case too. And then, or you can use the floor function or the ceiling function. So all 3 options will work out just fine.
for this, but you have like a 100 this item. If you divide it into 2, you're gonna have 50. Which 50 is gonna take the upper or the lower? And we're trying to find the middle one. So if it's 51, then you could have that, but the original number would have to be 101.
Yeah, you can just round it.
Okay.
Because each half is at the most 1/2 of the original. If you pick the right half, the quote-unquote right half, then you have 1 fewer than just the half,
Okay.
which works out even better. But 1/2 is already fine. So it will work out either way. So we'll get to that point. All right. So now we have this is our current algorithm, loop and loop. When k equals to a bracket m, we have to figure out how to calculate this value m. or the array does not contain this value. Now, when we say this array does not contain this value, it is not just the parts that we have examined. This is a conclusion that the entire array cannot possibly have this particular value. Okay. Last time we also used the spreadsheet to visualize, how we can shrink the potential portion of the array that can contain the value that we are looking for. So let's go back and take a look at that first, because it is kind of important to look at the visualization, and then we can work out the algorithm. This is the order of magnitude discussion. I can save it into today's folder. Just say complexity. That's the time complexity, which has nothing to do with the actual length of the program. This is the competition between me and Pat. Okay, so we'll save it into, once again, today's folder. We'll call it linear search versus binary search. That's also not what I'm looking for. What I'm looking for is binary search examples. This is the one that I'm looking for. I'm not sure how many people still remember this particular slide or this particular spreadsheet. Column A is the array. Okay, if I look at this portion here, this is the array. I did not spell out the index because that part is kind of not so important when we're trying to understand the mechanism of binary search. We're looking for a value of 8, and as the name binary search implies, it's doing some binary thing, which means we are comparing to the middle element. So the first comparison, okay, this is also important. You can see this entire area is yellow to begin with. This means before the first comparison, we consider the entire array to be quote unquote candidate to have that value. Okay, the entire array, the value can be anywhere within the entire array, and that's why in column B, which represents what do we know before the first comparison, the entire array. Okay, the value can exist in the entire array, and it can be anywhere within the entire array. Column C has one comparison. So the result after the first comparison, let me just tie my shoelace first. The first comparison compares to the middle element of the entire array, because the entire array may contain that value. That element turns out to have a value of 7. And 8, which is what we are looking for, is greater than 7. Now because of this, 8 is going to be greater than this element, as well as this element, because they are all sorted. And as a result, we can rule out everything from the first element all the way up to the element containing the value of 7. And that's why the highlighted region, or the pale yellow region, is now shrunk all the way down to only these 3, because only these 3 particular items in the array may contain the value that we are looking for. Is that part okay? Does everybody understand the key, or what it is representing, what this spreadsheet is trying to represent? Okay. Now within these 3 elements that may contain the value that we're looking for, once again we try to look at the middle one, the one that is right in the middle, which is this one. Okay? And it has a value of 11. And this is what happens in the second comparison. The second comparison picks up that particular element and compare that to the value that we're looking for. As it turns out, 11 is greater than 8. So not only do we know that this element does not match what we're looking for, but everything after that also cannot be possibly what we're looking for. And that's why these 2 elements are also eliminated in the process. So when you look at column D, it is representing these elements as well as these 2 elements. These elements, or these 6 elements, have now been eliminated. Now some I have compared directly, but many I can just infer from a sorted array that they cannot possibly contain the value that I'm looking for. Is that okay so far? Yep, go ahead.
So you're saying that in column 7, in row 7, column B, because it's not shaded yellow, are you saying that it's not considered as when you're not shading yellow?
It's not shaded in yellow because I can already conclude that it cannot contain the value that I'm looking for. So the parts that are shaded in yellow represents, it may still contain the value that we're looking for. Okay? And that's how we get to the third comparison, because now we're down to one single element that can possibly have the value that we're looking for, and then we compare to it, and as it turns out, it is also greater than 8 or not equal to 8. So at this point, I have eliminated everything in the array. Nothing in the array can possibly contain the value that we are looking for. So are we doing okay so far regarding the concept of binary search? From the perspective of we are narrowing down which part of the array may contain the value that we're looking for. Yep.
There's no mathematical operation for this. You're just demonstrating how this program would actually cut out search results until it finds the ones that get close to it, right?
There's an algorithmic way to do it. Okay. In other words, it is not mathematical, but it is it can be expressed as an algorithm, step-by-step instructions, so a computer can do it. Okay. Yep.
Now this works for binary searches, for
Assorted
numerical
array.
searches. Can we say the same? Does it use the same technique when doing alphanumeric searches, like searching for names?
As long as the array is sorted, this approach can be applied.
In other words, alphabetical order is fine.
Yep. You need the array to be sorted in the way that you are searching. In other words, if you have student records, then you can sort student records by last name, first name, student ID, and so on. So you have to make sure that however you're trying to locate a student is how the array is sorted. Are there any questions? Yep, go ahead.
Why is 10 bigger than 8 equal?
Sorry, say again?
Why is it the furthest number equal?
The first one?
No, 10 bigger than
This one?
8. Yes.
Because I'm comparing to this element. And that's the conclusion, 10 is greater than 8.
It will always stop until it's equal to it. And since it's not in there,
So I mean, it's just you can put it anywhere, like on the row.
I'm not sure what you're asking.
I'm just
but
asking that they are not in line. I mean, they are not following any orders.
there's a
The way it's
specific order.
searching.
Column B represents before the first iteration of binary search. This is representing after the first iteration. This is after the second iteration, and this is after the third iteration.
Okay.
So after the third iteration, you can see nothing is highlighted in pale yellow, and that means there are no candidates left that can contain the value that we are looking for, and as a result, we can exit the loop. Are we still doing okay so far? The other way to do this is for me to copy and paste the actual value and then change these guys to be greater than or less than. That may work out okay too. But what we're really trying to keep track of, in the first iteration, is where is the beginning and where is the end of this particular region in the array. In other words, we want to find out, we want to use a bookmark to represent this is the beginning and this is the end. After the first iteration, we want to remember this is the beginning and this is the end. After the third iteration, this is both the beginning and the end, and after the third iteration, then we have nothing left. So there won't be a fourth iteration because if I know for sure that the value 8 is not in the array, I can just exit and conclude that 8 is not in the array. Are we doing okay so far with this notation? Okay. Sorry?
I'm doing a lot better now.
Okay. So that means if I want to highlight it, let me see if I can easily. Yep, I can. It doesn't show the overbar. Is there even the overbar? Yeah, it's just very thin. I cannot. I have to do a custom, if I were to do it like this. But what I want to do is to keep track of, which part of the array can still have the value that we are searching for. So switching back to the algorithm, we'll add some more things to the algorithm. So revision 3 of binary search is going to do something like this. We'll introduce 2 more variables. One to keep track of what is the index of the first element in the array that may still contain the value that we're looking for. And then the second variable is to keep track of the index of the last element that can still contain the value that we're looking for. Okay, so I'll spell that out here in revision 3. B is the index, not the element itself, but the index of the element, of the first element that may contain K. Okay? And then E, which stands for end, is the index of the last element that may contain K. Now this is very important because B and E are basically acting as bookmarks. In other words, if you think about this as searching for a particular name in a phone book, because a phone book is sorted by names, right? So if I search by last name, it will be pretty easy because it's already sorted by that particular criterion. B is a bookmark, and E is also a bookmark, post-its, bookmarks, whatever you want to call it. And the pages that I need to search would be the pages in between these 2 bookmarks. Instead of ripping the phone book apart, whenever I do one comparison, I tear out one half of the phone book, I'm just moving the bookmark. I'm just putting these bookmarks closer and closer together because the region of the phone book or the pages of the phone book that may contain the phone number, that may contain the name that I'm looking for, is shrinking. And every time I compare, I can have up to one half of the choices removed because I'm moving the bookmarks closer and closer. Is that analogy working? Okay, so B and E are bookmarks. Yep, go ahead.
I was just gonna ask, so it's like if you're trying to go 1 to 10 or search for 1 to 10, E would be 1 and E would be 10 for the first iteration.
To begin with, yes.
Okay.
Exactly. The concept is right, except in arrays, the index starts from 0 to 9. In that case, when you have 10 elements. But you got the concept. You got the concept. Okay. Yep. Go ahead.
Generally, any binary search you come up with, the algorithm itself, we're always going to be tracking the indexes, and we're not really going to track the values themselves. We're going to track the indexes. We're not going to track the elements.
Correct. You have to keep track of the indexes and not the values, because the values you don't need to track. They're already stored in the array. So what you need to track would be the index, or where in the array can still contain the value that I'm looking for, and that's why you're only interested in the indexes. Okay. Yep. Go ahead.
So you're just narrowing the search each time, just making it shorter. You're making the possibilities shorter and shorter each time.
Yes. For each iteration, for each comparison, you basically eliminate one half of the possible choices. Sometimes one more than one half, because it depends on the actual number in the array, but you're guaranteed to be able to eliminate at least one half of the remaining choices. Okay. So are there any questions about this part here? What B is representing and what E is representing? No? Okay. Well, let's go ahead and see how we can initialize B, because you already kind of mentioned how we should initialize these 2 variables. What should be the index of the first element that may contain the value K before the first comparison? 0, exactly, because that's the index of the very first element in the entire array. What about E? It's the index of the last element in the entire array. Yep, bar A bar minus 1, because bar A bar is the number of elements in the array, but that's not the index of the last element, because we start counting from 0, and that's why the index of the last element is bar A bar minus 1. There we did it. Yep, go ahead.
Why isn't it K minus 1?
Sorry?
For
For E, why is it bar A bar minus 1?
versus K minus 1?
K minus 1? But K is the value we are searching for. It has nothing to do with the size of the array or indexes. Yeah. Okay. So let's see if we can understand, or we see if we can re-express this. Okay. Okay. Let's look at the definition of B and E. B is the index of the first element that may contain K. So B starts all the way at the beginning of the entire array. So from your perspective, it is on this side, okay? And E starts all the way on the other side. After each comparison, I will move either one, right? Okay, I can either move B or I can move E. But in any case, they get closer, right? So they can go closer, closer, closer. But even as they're getting closer, they maintain one particular relationship. When you compare B to E, as long as there's at least one element left to compare, how would you state the relationship? As in greater than, less than, equal to, that sort of thing? Not equal to 0. They can be 0. I mean, if the first element does contain the value that we are searching for, B and E can both be 0 at the same time.
E is greater than B.
E is greater than or equal to B. Okay?
At this point.
Because there can be exactly one element left. Okay? So let me go back to the spreadsheet and explain. Okay, so in this case, okay, let me just add one more column here for the indexes. So the indexes are going from 0 to 7 in this case. Oh, I missed one number, 0 to 6. Okay, so these are the indexes, and I will make it more clear. So these are the indexes. These are the values at those particular indexes. And this one has no particular meaning, so I'll just go ahead and clear formatting here. In the first iteration, this entire array may contain the value k. So that's why 0 is our B, and then 6 is our E. After the first comparison, we know that these 4 cells cannot possibly have the value that we're looking for, and as a result, B becomes 4, and E becomes 6. And then after the second comparison, we know that there's only one element left. Now, when there's only one element left, what is the index of the first element? It's that guy, right? In this case, it would be 4. What is the index of the last element? It's the same, because we only have one element left. And that's why the beginning and the end will still be the same. What do you think B and E will look like when we have nothing left? We break that relationship, right? We break the relationship that E should be greater than or equal to B. Does it make sense? Okay, yep.
It's convenient. Okay, it seems like all the examples you've been giving us these last 2 weeks have always been convenient that the last iteration has always been 1. And so it seems like there's always odd numbers, 7, 9, 11. What if it was an even set of numbers?
We'll deal with that. We'll deal with that later. But that's not really the most important part of the algorithm, because we'll just be off by 1, which is okay. Okay, but for the most part, that part is not as important. Because worst comes to worst, what we can do is to say, you know what, we want our arrays to be always of the size of 2 to the power of something minus 1. If your array doesn't have that size, we'll pad the end of it with the last value until it fills up the entire array. So we can always make an array the size that we want, okay? Without changing the fact that we cannot possibly find something that is not in the array, nor conclude that something is not in the array when it is in the array. Okay? So we'll deal with that little more minor problem later on. Okay. So if I were to create bookmarks here, then these two will have the bookmarks. It's easy. Turns out it has one particular choice here that can do that. I think you guys can see the horizontal lines, which marks the beginning and the end. So you can see how these 2 lines are getting closer and closer. After column E, or after the second after column F, which is the last comparison, these 2 lines will will go past each other. Okay. So in the algorithm, we can kind of express that and say we'll stay in the loop as long as there's at least one element left to compare. And that condition is guaranteed only when B is less than or equal to E. Oh, I take it back, because we're talking about when we should get out of the loop. So that's the flip side of this. When B is greater than E, then it doesn't make sense anymore. Is that okay so far? Because if the index of the first element that may contain K is greater than the index of the last element that can contain k, how many elements are in between? 0. Because there are no elements that can satisfy that requirement. Okay. Right. So we'll call this one, another iteration. This is a really important iteration too, because this really is the meat of binary search. Okay, so now we are on to revision 4. Revision 4 does not need to introduce any more variables. So what is left here is to say, yeah, but what are we going to do in the loop here? Well, if you want to decide what needs to be done or what has to be affected by the loop for each iteration, you have to look at all the variables in the condition, because at least one of those has to be modified in order for the condition to eventually become true. So we'll go take a look at these ones here, and we'll examine each and every name and say, can we change this? Can I change the nature of the problem and just say, no, you wasn't looking for 8, there's a 7 in the array, you were looking for 7 and it's in the array. Can I change the nature of the question? No. If I'm looking for 8, I'm looking for 8. I cannot change the key or the value that I'm searching for. So the loop cannot change k. Can I change something in the array A? You're looking for 8, it's okay. I'll overwrite the array, so now it has one element with a value of 8. No, I cannot do that either, right? What about B, E, and M? Sounds like M can be is something that we can possibly change. In fact, it is probably something that we want to change because it does control which element we are comparing to. Okay, and if you go back to this spreadsheet, you can see that we're comparing to one element here, one element here, and one element here. Maybe we don't know how to compute the actual index at this point, but we know that is changing over time. So we know that M is changing. And then we look at B, and then we look at E. One is the bookmark marking the beginning of a range in the array, and one is marking the end of the range that may contain the value. And you look at the spreadsheet here. This is B, this is E initially. This is B, this is E after the first iteration, after the first comparison. This is B and E, after the second iteration. So it seems like B and E can change as well. Now that gives us some clues as to what needs to be done inside the loop. Okay, we know we are going to change M, we're going to change B, we're going to change E potentially. So are we still doing okay so far in terms of analyzing, how to write the algorithm? And I think that's algorithm design is to analyze, starting with knowing that this is just a loop, and then you add, okay, when do we get out of the loop, and then you try to make it more formal. Okay, so we're going to copy and paste this. This is revision 5. What are we going to do in the loop in order to make this happen? Well, the first thing is, before we can change B or E, we kind of have to figure out what we are comparing to, because it is the result of the comparison that changes either B or E, right? So we have to know what we're comparing to. If you go back to the example in the spreadsheet, in the first iteration, we first decide that we are comparing to A bracket 3 in this case, which has a value of 7. So we have to determine M first, okay? What is the index of the element that we're comparing to? Based on that result, in this case, we moved B so that we only have elements 4, 5, and 6 left. Okay. So back to the algorithm, we know that we have to change M, to something, so that we can actually do some comparison. Okay, so we'll just put a question mark here, and then we say if A bracket M, has a particular relationship to the value that we're looking for, then we do something. I always put in an else here. Okay, so we'll just do it like this, step by step. This is revision 5. Okay, I know I have to do something about M. I know based on the relationship between M, A bracket M, and K, I need to do something. Okay, I cannot quite decide what to do or which one of B or E I'm going to modify, but I know that I have to use that to create a branch so I can decide what to do. Okay, so this is revision 5, has definitely is kind of vague and has some unknown stuff here. Okay, the question marks are unknown. Okay, so here's revision 6. In revision 6, I'm going to make this a little bit more solid. In other words, it seems like we're always moving to the middle part of the range that can still have the value k. Okay. If you go back here, initially this entire thing may have the value k, then we pick the middle one and compare to it. After the first iteration, this is the remaining part, then we pick the middle one to compare to. After the second iteration, we only have one left, which is also the middle part of the entire range, and that's how we compare to it. How do you compute the index of the middle one? Yep.
E minus E divided by 2, so you're taking the average.
B plus E divided by 2. Okay? Or you can say B plus and then open paren B, E minus B close paren divided by 2, but they all boil down to the same thing. Okay? So in this case, I'll just use the simple one, which is B plus E divided by 2, which is also average. Okay? It's just the average. Is that making any sense so far? Why I choose to calculate the value of m this way? I know the beginning, I know the end, I want the middle part. Hey, the middle part is really just the average. Yep.
So you're calculating m every time for every iteration.
Correct, because each iteration compares to a different element, so I have to recompute the index of the element that I'm comparing to.
So you're doing this for the elements inside the index, not the indexes themselves.
I'm not comparing to the index. I'm using the index to tell me which element I'm comparing to. Now that's a very important part, is when we deal with arrays, there are two numbers that we have to deal with. One is the index of an element. The index of an element is nothing more than the street address of a house. The value of the element is the content of the house. So you use the index to help you find the house, but once you find the house, the content is inside the house, and the content inside the house has nothing to do with the street address of the house. Okay, so you got to separate those two. All right. So we just specify a little bit more detail here, and we'll just work out one case here. Okay, we'll use our spreadsheet here as an example. In this particular case, when 7, which is the element in the array, is less than 8, we choose to move. Which one did we move? Are we moving B or E in this case? B. We're moving B, and B got moved to just one past 3, which is the index of the element that we're comparing to. So switching back to the algorithm, I can even do it this way so we can actually see a part of the spreadsheet. Okay, so we say that we can figure out at least one case. If the array or the element we're comparing to is less than what we are looking for, then we can go ahead and move the index of the first element to become m plus 1. Very good. Now if you forget the plus 1, the algorithm will seem to work, but then you can also end up in infinite loops, because it just doesn't have the last thing to make them overlap. Okay? So the plus 1 is extremely important here. Okay. Are we doing okay so far with this step? Now this step is really a generalization of what we observe in the example. Okay? And that's basically a big task in programming, is first to figure out how to do it by hand, and then you have to look at the steps that you do and try to formalize, or in this case, you're abstracting it. In other words, you're looking at concrete examples, and then you're trying to describe how you did it, using abstract steps. Okay, that's good. I'll call this, revision 6, done. The algorithm is not done, but it's pretty good for us, that we figure out how to handle one case. Okay, in revision 7, we'll try to handle the other case. The other case is over here on column E. I can shrink these columns a little bit so we can fit the algorithm next to it. And column C obviously doesn't need to be that wide. There we go, much better. All right. Okay, so we want to be able to handle the other case, because the next time in the second iteration, this was the beginning, this was the end. After one comparison, we move the end from here to here. Can everybody see that? You know, that's basically what we did. Okay, but what triggered that action? What triggered the decision to move the end of the range of the array that can contain the value k from where it was to an earlier point? It's because 11 is greater than 8. Okay, it's because 11 is greater than 8. 11 is the value of an array element here. If that is already greater than 8, it really says everything after that will be greater than 8, which means the element cannot be there. Okay, what we're looking for cannot be here, cannot be here either. Okay, so going back to the algorithm, it seems like I have another thing that I need to confirm, because if a bracket m is greater than k, we want to do something else. But why can't I just do it here? And then we just say, oh, we'll change e to m minus 1. This would be incorrect. Why can't we do it like this? Because there are actually 3 possible. Yeah, go ahead. Not exactly. Okay, the reason why we cannot do it like this is because if a bracket m is less than k, we really have 2 cases left. Okay, one of those is a bracket m is greater than k. What is the last one? What is the third one equal? They're equal to. Exactly. So we cannot do it like this, because when a bracket m does equal to k, it makes the condition false. Okay, let me just go back here. When a bracket m does equal to k, this condition is false. But yet in that case, I don't want to change e. I just want to get out of the loop. Okay. So that means I need to guard it and say else if a bracket m is greater than k, then we'll just go ahead and move e to an earlier point. Are we still doing okay so far with this code? So I'm just adding one more case to handle in revision 7 compared to revision 6. Still doing okay? Kind of. This is a more complex algorithm than anything else that we have talked about in this class. Okay. And we'll trace it too. Yeah, we'll definitely trace it. I'll make it your homework assignment. Okay, here's revision 8. Revision 8 looks at this, I think we're pretty much done. The only part that is left is, I don't really like using loop and end loop here, because I want to know whether it is going to be a pre-checking loop where I can check the condition before each iteration, or does it have to be a post-checking loop where I have to perform the action inside the loop and then I can check the condition and see whether I have to do it again. What do you guys think? Go ahead. Well, let's try to analyze the loop here. Okay, what is the value of m before the entire first iteration? Did I initialize m at all outside of the loop? No, m is not initialized, and yet it is used in the condition that we need in order to determine whether it's time for me to exit the loop or not. That is the indication of we need a post-checking loop. Because before the first iteration, m is not even determined. It is unknown, okay? Or it has a value that we don't really know. It is not initialized. So we cannot use a pre-checking loop in this case. We have to use a post-checking loop. Conversion to a post-checking loop is easy. We just change loop to repeat, and then change end loop when to until, and we're done. Any questions at this point? Yep.
The reason why m is not defined is because we haven't got. You don't answer my question.
And that is why we need a post-checking loop, because we need to go through the body of the loop to make m meaningful.
We don't get until we find out we need to.
Right. Now, of course, the next question is, what if M or what if A bracket M is K already in the very first iteration? Does it do any harm? No, it doesn't do any harm, because if A bracket M does equal to K, do we do anything to B or E inside the loop? No, absolutely not, which is fine, because that's exactly how we want it, is not to modify B or E unless we need to modify them. Okay. All right. So now we are almost there. Okay, we are almost done. Okay. Revision 9 only has one job to do. It has to conclude, did we find it or not? Just because we got out of the loop is not really good enough, because it simply says, yeah, I can confirm that either we found it or we did not find it. But which one is it? Okay, if you look at it from the perspective of someone who is going to run this algorithm, knowing that you can get out of a loop because you can conclude, yes, the element or the value is in the array, or no, the value is not in the array, is not enough, because I already know it. I know that the value is either in or it's not in the array. That part I already knew way before I ran this algorithm. I want to know which one it is. Okay, so how do I make that conclusion? The relationship between A and B. Exactly. So I'm going to use a template here, and this is actually how I write my programs. Okay, the funny part is most people look at this and go like, "Wow, that's kind of lazy," because you're not doing anything here. When I write my algorithm in C, C++, Java, PHP, Perl, doesn't matter what the programming language is, I always write in the skeleton of a particular control structure, like a conditional statement or a loop, and then I go back and fill in the details. Because this way, I don't have to worry about, oh, where am I supposed to end this thing here? What is the indentation of the end? If I do it right away, the indentation is easy to figure out. And most editors will have the AI or the auto indent feature where the indentation of these 3 lines are automatically aligned. Now I can go back and say, well, we need one branch to, okay, I'll just put in quotes here, conclude K is in array A, and then the other one obviously is the other option, to conclude K is not in A. Okay. So knowing that these are the 2 branches, how do I confirm K is in A? There are 2 ways to do it. You can pick either one. K equals A. Yep. That will do it. As it turns out, in this case, you can use BE, the relationship between B and E, to confirm it is there or not.
This one seems simpler though.
Really?
If it is there, then it is there. But if it's not
But you can also do it the other way. You can say, as long if I get out of loop, and by the time I got out of the loop, B is still less than or equal to E, then the element is, K is in A. You can also use that approach. So in this case, you can pick either one. It doesn't matter which one you pick. All right. The binary search is all done. I'll make your homework assignment. No homework.
This kid in your class is the only class I've ever said yes, homework, and practice.
Yeah.
Well, practice is useful.
What are you gonna have it do?
We'll do it after spring break, and that's fine.
Just wanna make sure.
Most people will probably forget it by the time by the Tuesday after spring break. Everybody's still like, I knew that was something I was supposed to do.
I just wanna make sure it wasn't during.
No, I wouldn't do anything like that. During spring break would be kind of. I don't think the college allows that.
Really?
Yeah, because okay, so before the semester starts or right after, even if it's 1 day or 1 minute after the semester ends, we are not allowed to use any work submitted after that time for grading purposes. That's just not allowed at all. But whether that rule is enforced or not is a whole different story. Or how it is enforced.
It's just always fun to have a few minutes on that.
Yeah, go ahead.
Is this the most efficient pseudocode for a binary search that we could come up with?
They're all about the same. Yeah, they're all about the same. Oh, I forgot one thing. I forgot one thing, I'm sorry. Okay, what if the size of the array makes it so that b plus e divided by 2 gives you something 0.5? Okay, we haven't really addressed that particular part. So there are different ways to do it. You know, this is one quick and easy way to do it. I just put a floor around the whole thing. Okay, the floor of something is the largest integer that is still less than or equal to whatever that you're taking the floor of. That's a mouthful. Okay, I'll just write it out here, and then we'll digest it slowly. Okay, okay. So the floor of x is the largest integer that is still less than or equal to x. Okay, which is a really long way to say something that's kind of intuitive. It's just rounding down. Okay. Now, rounding down seems kind of intuitive, but there are tricky cases too. It doesn't apply to this particular program, but nonetheless, it is still tricky. Okay, so I'll just go ahead and ask you a few things. What is the floor of 2 itself?
2.
That's just 2 because 2 is the largest integer that is less than or equal to itself because it is an integer to begin with. Okay, so that's easy. What is the floor of 2.1? It's just 2. What is the floor of 2.7? 2. All right, last one. Floor of negative 2.7.
Negative 3.
It's negative 3, not negative 2. Okay? Because we're not just getting rid of the fractional part, we're rounding it down all the time. So when the number is negative to begin with, you have to round it down to the next negative value on the negative side. Okay? So this is not the same as, there's another function to get rid of the fractional part of a number. This is not doing exactly that because it's always rounding, except it's just rounding down. Okay? Sorry?
You're talking about ceiling?
Ceiling is always rounding up. Okay? This is always rounding down. There's another function to only get the integral part of a number. I cannot remember the name of that. You know, it probably wasn't that important. Okay. So, yep, go ahead.
So binary search in general. Is binary search the most efficient search
Algorithm, yes. Assuming the array is sorted, okay, it's not indexed in any other way, binary search is the most efficient way to do it. Because they can actually prove that there does not exist an algorithm with a time complexity of less than the log of RA bar when it comes to searching a sorted array. It can be proved. Yep.
So for other types of indexing, you'd have to sort them before you did
It's not exactly sorting, it's actually throwing things into different bins. So you're kind of cheating in that case because, okay, let's say we are looking at names, okay, so alphanumeric or just alphabetical names. So what you're doing is you first create 26 bins, one for each letter in the alphabet, okay? And then based on the first letter of the name, you know which bin you look into, right? Now within that bin, guess what you have? You have 26 smaller bins. And that's based on the second letter of the name. And then each one of those bins, once again, has 26 bins inside, and then more 26 bins inside. So this way, when you look at each letter of a name, just one by one, you are traversing basically, it's just like folders, right? So you're just traversing one level of folder at a time, and that way, that is actually the quickest way to see whether something is there or not.
It has to be set up that way in the first place.
But it has to be set up that way, and it is not the same as a sorted array. So given that you only have a sorted array, which means it's not using the buckets, the 26 bucket trick, this binary search is the quickest, the fastest search algorithm. There may be another one, or there may be other ones that are also having a time complexity of log of the size of the problem, but nothing can be faster than this. Okay. Now, some of you, how many people are going for the computer science program? I think there should be at least one half of the class doing that. No. Okay. You guys are all jumping ship because I'm teaching this class. Okay, but if you're in a computer science program, eventually you will take cisp300, which is data structure. Now in data structure, there's a concept called a hash table. Now in the hash table, it's even better than the buckets, okay, the 26 bucket concept, because what happens is if you only have, let's say, 300 items to store, you will have a hash table of maybe 1,000 items, okay, and then using a hash value, you can locate the bucket that contains the value that you're looking for. Okay, so in those cases, the lookup time is what we call a constant lookup time, or big O of 1. Okay, and it cannot go any faster than that. But it does require the concept of a hash table. And hash tables are interesting. They're very practical. They're used in compilers, left and right. But they also have problems. Okay, they're not sorted in one way, and it's also hard to enumerate all items within a hash table. In other words, if you ask the question, instead of asking the question, is this item in the hash table? And instead your question is, print all the items in the hash table in a sorted order, it's difficult to do it with just a hash table. So the hash table is good for one thing, which is just look up and confirm something is there, but it's really difficult to do some of the other things we can easily do with a sorted list. Yep.
Isn't that how searching on the cloud cloud computing works?
You mean like Google search and stuff like that?
Yeah, like OpenStack or whatever. OpenStack. I just watched the videos about OpenStack, so it's like,
I do not know, but Google search definitely is way, way, way beyond these basic search algorithms. They index things in completely different ways. Because otherwise it would be impossible. It's really hard to locate a particular web page within a fraction of a second. All right, so let's go ahead and make your new homework assignment, and you can see how I make the homework assignments. It's no secret. I don't get it from a textbook CD-ROM, that's for sure.
It's automatically a good thing.
What?
That's automatically a good thing.
Not from a textbook?
Yes. Textbooks are awful.
All right.
There has to be a better way.
Well, there are a lot of resistance to do that because the publishers need to make money. Well, need to make more money. There's always more.
I like the way you do it. You like make your own material and post it like for free.
Yeah, some people hate it.
Who could hate free learning material?
Well, because you only have one source in that case, so you don't really have an alternative to say, okay, but I want it to be explained in a different way.
That's when you take terms that are in the material you have and you Google them.
You can do that. That can be used. All right, so this is the algorithm, and then I'll just say found gets a bracket m equals k. So instead of using a conditional statement to say conclude this and conclude that, I'm just using an extra variable called found, which is Boolean, because you can see that it's going to store a true or false value. If found is true, guess what? It is found. And if found is false, guess what? It is not found. Okay, so that's our conclusion. This is how we store the conclusion of the entire algorithm. And I'll even be kind enough to adjust the indentation. I mean, the spreadsheet is really great because I can pick not consecutive lines and indent those lines. If I use a plain editor, I will have to go to each line and indent each one individually. All right, so here's a big hint, especially for people who are here and also people who will watch the video clip. You might want to change the algorithm and just break it, okay? Get rid of the +1 on line 6, get rid of the -1 from line 8, And then just run the algorithm a few times and see what happens, especially when you're looking for something that is not in the array. Okay? Because you will get an idea of, well, how can that +1 and -1 be so important when the floor versus the ceiling versus round on line 4 doesn't make any difference at all. Okay? So you might want to try that out once. Okay? Just try that, looking for a value that is not in the array, and then see what happens to the algorithm. Okay, I'm not going to tell you what, actually I told you what already, but but most of you probably would have forgotten that already. Yep.
Are you going to provide the array as well?
Sorry?
Are you going to provide the array?
Oh yeah, absolutely. This is just the algorithm, and then I'll give you the array as a starting point. So you need comments, you need line number, and then you need the 3 variables. K, it has to be given. B, E, and M can be determined during runtime, and then you have array A. And I'll give you an array of 4 items. Okay, so it doesn't divide nicely. Okay, so we have 4 items, and amounts of 4 items. The values don't really matter that much. -4 or -5, 3, and then we have 10 and 11.
Since we're using found, would we list that as a variable?
Oh, yeah, that's one, 2. Now, after this concept, after arrays, we'll be moving on to subroutines. Now, that is also a very interesting discussion. We'll get started on that today. But first, before that, I'm going to have to give you your homework assignment. This is the precondition. B, E, and M, they all start with unknown values because you're going to initialize those. Same thing with found. And K, I have to give you because you have to know what you're looking for. So in the first one, I'm going to give you, something that's easy. That's easy. Super easy. And then the comments, I think you need a little bit more space. You can always adjust these things yourself. I mean, if you're running out of space on comments, just drag it and make it wider. All right. So this is your first case. And I'll get rid of this. All right. Are there any questions about the starting point of the first trace on sheet 2? Okay, I'm looking for 3, and the array is already initialized as a precondition. And you just have to go through the algorithm and find out, how it gets things done. And now I can just say, hey, is there a copy? Yep, copy. The end position, call it sheet 3. See, I like this feature a lot. So the next one, I'll use exactly the same array, but this time I'm looking for -6. Okay. And I'll do the same thing again. Let me see if I can do this. Select 2 sheets at the same time. And then copy. Can it copy both at the same time? No. Yes, it did. Oh, nice. So I look for 12 in one, and then I'll look for 13 or 12 in the last one. There we go. That is very nice.
We got 2 of them that we're looking for the same value.
Yeah, sheet 2 and 3 or copy sheet.
Oh, okay.
2A.
Okay, this one is supposed to be 10. New. Well, let's look for 7 in between. And then 12 at last. Okay, that works. Just have to rename. This is actually 4, this is 5. Minor details. This way it's harder to miss, because if I give you like a 3 and then a 3_2, it's easy to miss one. This way, it's just counting 2, 3, 4, 5. All right, and then I'm gonna do this, changes, record, not show it, so it won't be distracting. Save the file. Put in even into today's folder, so I have a copy too. This is line research homework. That's it. See, now you can make homework assignments for yourselves.
So everybody will do that.
That would be kind of fun because if I can, that's the way to teach this class. Make your own homework assignment, but instead of making your own homework assignment, every homework assignment is like a competition. So you guys will turn in okay, I think this will be great as the next homework assignment. I'll pick one. If there's one that I think is really great. If none, I will have to make my own. Okay.
Hope you can answer your own problem. Hope you can answer your own problem.
Yes. All right. So
You can always give like a form, like an outline format, and then people just fill in values, and they can add loops and stuff like that.
Or you fill in your own grade.
All what you could do is you could have people make their own homework assignments and then just switch them up. So someone makes a homework assignment, you give that to someone else.
Well, my son has this. He's in elementary school, so his teacher said, okay, this is going to be a self-grading homework assignment. I think it was music. Okay? So they're supposed to give themselves a grade for themselves. But then the teacher said, but if I look at your grade and I think you're not you're supposed to be getting that grade, I'll give you one grade lower than what I think you should be getting. Okay? Now that's a really interesting statement, because now the kids cannot just say, oh, I'm an A student. Because if a C student thinks that he or she is an A student and the teacher disagrees, that student would end up with a D, not even a C, because that will be like one grade lower than what that student is deserving. So all of these kids now have a much realistic estimate of their performance in that class. I think that was interesting. Download this file, starting my file. I'm doing this from learning this from the accessibility class that I'm teaching. Does anyone know what is accessibility?
Yeah. Like making stuff available to people with disabilities.
Yes. Particularly people who are not sighted, people who cannot see, people who cannot hear, and so on and so forth.
So what do they cover in those classes?
How do you make HTML documents that can be read by a screen reader, for one? Yep.
No, it's interesting. I never thought about that before.
It is actually kind of interesting in a way even for people in this class, because instead of, how many people think that HTML documents on the web are mostly hand created or hand generated, or do you think it's mostly generated from a database and you just use a script to pull content out of the database and package it into HTML files?
It's a lot of scripting.
It's mostly from scripting, right? So if you want something to be accessible, that is what you need to do, is to change the script that is generating the HTML documents. Okay. The algorithm is in sheet 1, trace sheet 2 to sheet 5. Okay, so I think by now most people know what to do with this. And we'll move the due date to 1 week after next week. So that's going to be April 2nd, right?
Yes.
Do the same thing here.
Glad it wasn't my birthday.
Sorry?
I'm glad it was not my birthday. It's something to do.
And we'll make it due at 10:30, right before the class. No. I don't need the email for every submission. Online text file, yes, one file, that's good. 5 megabytes should be more than enough. Feedback, yes. And we'll make the point values. Since we have 4 traces, but let's make it 40 points.
Are there like blind programmers? Are there like blind programmers?
I'm pretty sure they are. All right.
They make braille keyboards.
Huh?
They make braille keyboards, so it's entirely.
Oh, I forgot one thing, or at least one thing, because it won't let me. Uh-oh. Did it go through? Yep, it did. Okay, here we go. All right, so now you have your homework assignment. Yep.
Will we be able to edit the document if it's threaded? Like if I feel like I'm
Yes,
accepting-
absolutely. Yeah, since I did not say you have to submit, use the submit button, which basically means I'm not going to change it later on. As long as it is before the due date, you can always download it from the link, because once you upload, it will give you a link to your file. You can use that link and download the file back and then change it and then resubmit it. Yep. Sorry?
Got to get access to multi-class last semester. Probably the most interesting thing I learned about was installing hidden links where the reader can bypass and jump
Oh, yeah.
on the page. That
Yep.
was interesting.
Yep, definitely. All right, so we are done with arrays, okay? Now we are moving on to subroutines. Now subroutine, which is in topic 9, you can see how big this one is compared to the other ones. It's because subroutines is a very, very important concept. This really goes back to the top-down design concept, where we break a program into large chunks, and then each chunk is broken into smaller chunks, and so on. So subroutines is kind of hard to introduce because it's difficult to explain subroutines without actually just showing you the mechanism first. Okay, so I'll show you the mechanism, and then later on, we'll go back and say, okay, how is that useful? Okay, when we're writing programs. Okay. All right, so we'll go ahead and start with something simple first. Okay. So we'll go to new spreadsheet. Okay. A subroutine is defined in this class. It's defined by the block like this, define sub, and you give it a name. Okay, so in this case, I can call this subroutine XYZ. Okay, XYZ is the name of a subroutine, and inside the subroutine, you can put any code that you can otherwise put into your existing programs. In other words, you can have loops, conditional statements, assignment statements, and so on and so forth. Okay, so you can put anything you can normally put into a program into a subroutine. Okay, so in this case, I'll just do something relatively simple. X gets x plus 1, nothing really fancy, and I use this to end the definition of a subroutine. So the syntax in this class, the pseudocode, the syntax of a subroutine is really easy. Define sub, give it a name, and define sub to mark the end of a subroutine. Okay. Are there any questions about this part of a subroutine? It is basically a chunk of code that has a beginning and an end, and it has a name. That's it. Okay, for now. When you're outside of a subroutine, you can. Okay, first of all, x needs to start with a particular value, so I will say x gets 0. And then here I'll say invoke subroutine xyz. So I'll just skip the sub, I'll just say invoke xyz. And I'll just call that the end of this program. Maybe I'll just have one more thing to do. X gets x times 2. Okay, there we go. This is the entire program. Now what is interesting about the subroutine is the code inside the subroutine remains quote unquote dormant, or it doesn't do anything until the subroutine is invoked. It's kind of like the definition of a subroutine is like a definition in a dictionary of words. Okay, so until you're reading something that has those words, nobody's going to go to a dictionary and start to read the dictionary. Or most ordinary people won't do that. Okay? There are people who do that, but most of us probably don't have time to do it, right? So the only time you look up a dictionary is when you're reading something else and you encounter a word that you don't understand, or you think, okay, I might know what it means, but I want to look up the actual definition. So that's the only time you look it up. So when you look at define sub, xyz, and define sub, that is just like an entry in a dictionary. It is defining XYZ is a subroutine, it does this. In this case, it's really simple, but in other cases, it can be very long and complicated. But it doesn't do anything until you make use of XYZ using the invoke word. Okay? The invoke word is just what I choose to use in this class. In most programming languages, you just say XYZ, X open paren and close paren, and it will automatically trigger that, the execution of the subroutine. Okay. So let's go ahead and take a look at the trace of this algorithm. So let me save it first, give it a name. We don't have any conditional statements. There are no conditions whatsoever. You can start with just line number. There's a variable x, and the precondition is we don't know anything about x because we are going to initialize. Where do you think I should start the execution of this program? Because remember, the definition of a subroutine is just like a definition in a dictionary. So what do you think is the first line that does anything useful? Go ahead. Line 4. Line 4. Yep, that's it. Yep. Exactly. So in this program, we don't start with line 1 anymore. We start with line 4. In other words, when you have subroutines in a pseudocode program, like the one that we are dealing with here, you start with the first line that is outside of the definition of subroutines. Are we doing that? Are we doing okay with that concept? Now that is the same behavior in most scripting languages, like Perl, PHP, they all behave the same way. You can interleave definitions of subroutines within a program, but the execution will skip the definitions of subroutines. Yep.
So this would be kind of like the same as a function in PHP?
Yes, it is the same as a function or procedure, depending on the language. They call these things differently. A subroutine, a function, a procedure, they're all referring to the same thing. Now there are quote-unquote technical differences between the term function and a subroutine, or function versus procedure, but that difference won't make any sense until we get to return values. So for now, we are not going to make any differentiation between those three words. Yep, go ahead.
I'm a little confused. I thought a subroutine was a program, a mini program within a larger program.
I would call it a chunk of code with a name within a program.
Okay, that little chunk of code, shouldn't line 4 be right before line 2? Would you want to define or initialize X?
No, because remember, line 2 is inside the subroutine. It remains completely dormant until we invoke the subroutine. So it's okay to have line 1, 2, and 3 to be anywhere within this program. It can be all the way at the end if I wanted to. It just has to be somewhere so I know what it is. Yeah. And there was another hint. Go ahead.
Oh, what about Visual Basic? They have a structure module, or is that like what we're doing here? Subroutine?
In Visual Basic, a module is kind of like a library of subroutines. So in Visual Basic, if I understand correctly, a module is basically a collection of variables and also definitions of subroutines. Yep, go ahead.
So, like I've used subroutines before, but they've been different programs entirely. And
Okay.
Is that more like compiling then? Where you have like, say, 3 different documents and one document refers to 2 other documents?
You can have that. I mean, the subroutine can refer to each other. And you can also have one subroutine per file, or you can have like 20 gazillion subroutines in one single file. It all depends on the programming language and also the nature of your program.
So it's all still subroutines? It's not
They're all subroutines. As long as you have a chunk of code that has a name, and you can say, oh, I want that code to execute now, and I want it to execute again, that is still a subroutine. Conceptually, those are all subroutines. All right, so line 4 is pretty easy. Okay, when we execute line 4, x gets changed from whatever it was to 0. And then we execute line 5. Now, this is where things get a little weird. Okay, because what we want to do, I'm going to illustrate the effect that we want, and then we'll come back and say, yeah, but how do we make that happen? Okay, so what we want to do is to say on line 5 it says invoke XYZ. What do you think it should be the next line that we want to execute? We want to execute line 2, right? Because we're basically calling a point, the subroutine, and say, oh, do your thing. Okay, subroutine XYZ, do your thing, which is something that we do on line 2. And what do you think should happen after line 2? Where do I go next? Because line 2 is the only line inside the subroutine XYZ. Okay, so we want to go back to line 6, right? Exactly, because when a subroutine is done, I don't want the entire program to be done, because the whole idea of invoking a subroutine is I'm just going to offload, or I'm going to tell someone else to perform this particular task. But when that task is done, I want to resume control and continue the execution of the program. Is that part okay? Okay, so after you invoke a subroutine, after the subroutine is all done, I want to continue the original flow of the program. And so that whatever is after the invoke, I want to finish it. So I want to continue on to line 6. Now on line 2, we know that x is going to be 1, because we're adding 1 to x, which was 0 before that. On line 6, we want to multiply x by 2, so x becomes 2. And obviously, after line 6, we get to post, because there's nothing else after line 6. Okay, so now the question is, but how can we make this happen? Well, it seems pretty easy. Okay, maybe at the end of a subroutine, like in this case, we always go to line 6. Okay. We'll just go ahead and save this file, and I'll give you another file. We'll call it subroutine 2, with one minor change in this program. Okay, in this particular version, we have 2 invoke xyz. Okay, which kind of throws a wrench into the whole thing that we were just talking about. Okay, so x gets x times 2. And then we go back to the trace here. Right? It's kind of like, whoa, okay, what do we do now? Okay, after lines, okay, let's see here. We continue execution on, I messed up. No, this is right.
Yeah, just not 2.
Okay, so I'm on line 6 again. Okay, the first part of the program is identical to the one before. So up to line 5, I'm still okay. Line 5 is the end of the execution of the subroutine. After that, I move on to line 6. Line 6 is another invoke xyz. What do you think I should do? Go to line 2 again. Okay. Now after this time going to line 2, where do I go to? I have to go to line 7. Now we have a little bit of an issue here, because it seems like when I'm at the end of a subroutine, I'm not always going back to a certain line, because where I'm going back to depends on who got me into the subroutine to begin with. Now, how can I remember that? That's an issue. So we'll just go ahead and finish this program. Line 2 is going to add 1 to it. Line 7 is going to multiply this by 2, which means 2 times 2 is 4, and then we get to post. Okay, go ahead.
Well, couldn't you just always say that you always go back to the next line that's after the invoke coming?
Okay, but you still have to remember the next line of what, right? Okay, I'll give you one analogy, okay, because there's not enough time to finish the entire mechanism, and I would rather not talk about it, and then you guys just absorb half of it, okay? But I want to give you this analogy. You guys can kind of think about it and then relate it to what a subroutine is going to do. Okay, so here's the analogy. Let's say I have a car that other people want to borrow from. Okay, let's say I have a truck. Okay, everybody wants to borrow a truck. So I have everything set to my own settings, right? My mirror, the seat height, the radio stations, and everything. Okay, I got my CD into the CD player and stuff like that. So let's say John borrows my truck. Okay, and decides John is a different person, taller, shorter, wants to adjust everything, radio stations and whatnot. Okay? And then John decides, and John has a friend, Peter. Peter decides, I want to borrow your truck too. And I said, yeah, it's okay, let Peter have it, okay? And then Peter decides to change the radio stations and everything else, okay? And when Peter returns the truck to John, John gets all upset, right? Where are my original settings? The radio settings and everything is just not right anymore. Okay? And then when John returns the truck back to me, I'm upset too, because everything has changed. So what do you think is one way to solve this problem, other than not letting anyone borrow my truck?
Pass a message.
Pass a message. Go ahead.
Where it was some kind of a reminder.
Some kind of a reminder. Very good. Okay, so I need some way for John to remember my settings, and then when John is lending the truck to Peter, John also needs to say, okay, Peter, you better remember all the settings, because when I get a truck back, I want everything back to what it was, okay? So we need a little notepad. How many pages of the notepad do we need? Let's say we need 1 page for all the settings. In this case, we need 2 pages, right? Now, I don't need my own page because the truck belongs to me, so I can rightfully expect everything to be back to my settings when the truck is returned to me. But when I lend my truck to John, John needs to kind of jot down some notes, right? Okay, the seat height was this setting, and then the radio stations are like this, and this is the CD that was in the CD tray originally, and blah, 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 okay? When John is lending the truck to Peter, then Peter has to use up a second page of the notebook to write down the settings, not of mine, but of John's, right? So Peter drives the truck, when he's all done, he returns the truck to John. But before Peter returns the truck to John, what do you think he has to do? Reset all the settings, right? But it's okay now because it's all written down. And then John continues to drive the truck for a little bit more time, and then when he returns the truck to me, he has to do the same thing. Because John has his own page of the settings, which is mine, okay? Can you guys see the relationship between this story and subroutines? So subroutines need some place to remember where am I supposed to go back to when I'm done, okay? And nowhere in these 2 traces did we mention anything about that, okay? I don't like things that are not visual, that cannot be seen, because I like everything to be spelled out in this class. So on Thursday, we'll actually derive a mechanism to visualize how all this stuff is actually memorized, okay? I'm sorry I overrun a little bit, but that's kind of important. I'll see you guys on Thursday.
Very glad that I have